This is Alessandro Boaro, and I'm going to be discussing our chapter Artificial Intelligence and Big Data in Neurosurgery by Alessandro Boaro, Marco Mammi, and Omar Arnaud. The objective of this chapter is to understand the role and potentialities of artificial intelligence and big data in neurosurgery. I will start providing some useful definitions and will then explore some practical applications which have the ability to advance the state of the art in diagnosis, treatment, follow-up strategies, and training in neurosurgery. I will also discuss limits and risks related to the implementation of AI and the use of big data. And finally, I will provide a simple guideline for neurosurgeons who might be willing to start working in the field and briefly talk about what to expect from the future. The term artificial intelligence can take on a variety of different meanings. The most comprehensive definition refers to the ability of a machine or computer to use available information and reason in order to solve problems and make decisions. In a comparison with humans, where this process is made possible by the use of brain cells, memory, and abstract reasoning, in the case of a computer, the same goal would be pursued by means of processor units, digital memory, and logic. When AI techniques are applied to solve a specific task, for example, recognize a picture or play a game such as chess or Go, the term used to identify the computer's ability to learn that task and improve its performance in doing it is machine learning. Depending on the type of information the computer is provided with, the learning activity is distinguished in two main categories: supervised and unsupervised learning. These two approaches present different modes of implementation, as well as different goals. In supervised learning, the computer is provided with both the input and the output of interest, and its goal is to learn the best set of rules that allow it to associate the input to the correct output. This set of rules will then allow the algorithm to produce the best output once it is exposed to a new, previously unseen input. You can, for example, train an algorithm to recognize the picture of a car when it sees one. Two main types of applications are empowered by supervised learning: classification tasks and regression tasks. Classification algorithms assign the input to one class of a specified set of categories, whereas regression algorithms predict continuous variables as output. In the case of unsupervised learning, the computer is provided with unclassified data. The big difference with supervised learning problems is that in this case, the output is not known at all, even by the researcher who is training the algorithm. Here, the aim is to exploit the algorithm's superior computational power to unveil potentially meaningful and useful associations that will be later assessed and further explored by the researcher. These problems mainly deal with clustering activity, where the algorithm is asked to categorize the input in different classes based on the features it learns. You can, for example, design an algorithm to search for potential associations within a specified dataset of genes with regards to a specific disease. The term big data generally refers to data characterized by three V's, as in high volume, meaning the production of great quantity of data; high velocity, referring to the high speed with which such data are produced; high variety, identifying the high heterogeneity both in terms of content and presentation format, which can be highly structured, semi-structured, or totally unstructured. Two additional V's have been added over time: veracity and value, where the first relates to quality of the data that needs to be as high as possible, and the second refers to the ability to translate this wealth of information into successful business opportunities. Examples of big data are the ones produced by satellites and weather stations, or the data produced by the stock market every day. It's clear why AI and big data are absolutely interdependent and are basically the two faces of the same coin. In fact, the clever use of big data for training purposes allows the development of ever smarter machine learning algorithms, while, in return, the application of AI techniques has the potential to unveil unprecedented insights hidden in mountains of data, which would be otherwise undetectable with traditional analytic techniques. The reason why AI and big data have become extremely popular over the recent years, particularly in medicine, is that we only recently had at our disposal enough computational power to effectively run complex AI algorithms and at the same time manage the enormous quantity of data we produce every day. Within the medical specialties, neurosurgery is particularly well suited for AI applications and to work with big data. In the neurosurgical practice, we produce every day a lot of different types of data that perfectly qualify as big data. These are radiological imaging, pathology and molecular data, free text as reports, history of present illness or progress notes, longitudinal traces as ICP or EMG. Finally, ever more patients, not only in neurosurgery, rely on their personal devices to track their level of activity or store medical information. With regards to the role that machine learning techniques can have in neurosurgery, we need to consider the areas where improvement is needed and where these techniques can have a significant impact. There is definitely a role for algorithms using supervised learning in automatizing repetitive and time-consuming tasks, as for example the segmentation of normal structures or tumors, useful for navigation purposes in oncological and functional surgery. The analysis of longitudinal data trends as EEG or ICP can help in predicting the occurrence of a significant medical event, and doing so empower prevention strategies. With regards to treatment and training, robotic surgery, augmented and virtual reality have the potential to boost the training of neurosurgeons as well as refine their touch and increase precision in unprecedented ways. The potential for application of machine learning techniques in neurosurgery is vast and can apply to every step of patient care and professional training. I will now provide some examples of possible and actual applications of machine learning algorithms in diagnosis, treatment, follow-up, and training in neurosurgery. Classification and regression algorithms can help to improve our diagnostic abilities. For example, algorithms have been developed to try to extract histological and molecular information directly from MRI images of tumors like gliomas or meningiomas. An ambitious but real goal that these algorithms pursue is to realize the so-called virtual biopsy, where the algorithm will ideally be able to identify specific lesion features traditionally only detectable through the pathology exam or molecular analysis. Obtaining such information in a reliable way with no need to directly analyze a tissue sample would allow a more tailored and informed decision process, assessing the actual need for a surgical operation, and doing so, unnecessary risk would be reduced at the minimum, and the probability of success of a therapeutic plan would be maximized. Other algorithms have been developed to extract meaningful patterns from longitudinal data from EEG or ICP monitoring, allowing the prediction of seizures or the occurrence of a sustained increase in the ICP. Segmentation algorithms are special types of classification algorithms. They are trained to recognize a structure of interest, which can be normal, as for example the brain itself, or pathological, as for example a tumor, and provide a 2D or 3D mask of that structure as output. These models are becoming extremely good with accuracies over 90% compared to the work of a human expert. The implementation of these algorithms would provide a mask to be used for navigation purposes, as well as information on tumor volume, composition, extent of resection, growth rate, in an objective and very precise way, in a matter of seconds. Natural language processing, or NLP, refers to the ability of a computer at extracting relevant information from free text. These techniques have the potential to hasten many processes, especially in the field of population surveillance and early diagnosis, as well as in the execution of retrospective research. These types of algorithms are very powerful in time-consuming tasks as chart review. NLP algorithms have been successfully designed to assign pediatric epilepsy patients to surgery with performance comparable to board-certified neurologists and at an earlier time. Another study reported on an NLP algorithm which showed an increased ability compared to traditional surveillance method to identify surgical site infections. AI can have a considerable impact also in the way surgical treatment is carried out. The use of robots as surgical aids is not new, but is undergoing a constant evolution and refinement. Perhaps the most frequent application in neurosurgery of what can be considered a robotic instrument is radiosurgery. External beam radiation therapies rely on preoperative segmentation of the target on MRI and/or CT images. Robotic instruments specifically developed for stereotactic radiosurgery are now standard of care for a wide range of procedures. Another field where robotic arms have been implemented with success is spine surgery, particularly for pedicle screw placement. Other types of surgical robots and potential applications have been proposed, but didn't achieve widespread adoption. An interesting, different concept of surgeon robot is the one adopting a handheld robotic instrument which can apply variable counter force according to its vicinity to blood vessels. In this case, the main goal of the robot is not to perform a specific action with increased precision, rather restrain the surgeon from dangerous maneuvers. An interesting technology in its early development and application in neurosurgery is augmented reality. In a discipline where considerable efforts are continuously made to improve the ability to see, let's think about the operative microscope, the endoscope, as well as navigation systems, augmented reality as the process of enriching reality with additional virtual contents can be considered a natural next step in the evolution of visualization. In particular, the use of AR would allow the surgeon to keep the focus into the surgical field, avoiding the need to shift attention to a 2D screen and back. Spine surgery is again the field where great efforts have been directed in bringing this technology to the OR, with the first systems for pedicle screw placement guidance being cleared by the FDA to be used on real patients as we speak. Additional AR applications to improve navigation and guide resection of tumors as meningiomas or gliomas have been developed, as well as solutions to improve visualization in neurovascular surgery, with the aim to better visualize vital structures as optic nerves and carotids. The possibility of analyzing big data with statistical learning and machine learning is now promising to make more precise and personalized predictions compared to traditional statistical techniques. Machine learning models have been investigated to predict outcome of patients with a range of diseases of neurosurgical interest, from epilepsy to tumor and from trauma to vascular malformations. Several studies reported on machine learning models that could accurately predict seizure freedom after surgery for temporal lobe epilepsy. Prediction of survival of patients with brain tumors, gliomas, or brain metastases has also been investigated. Input data were most frequently MR images with some degree of clinical information. Extent of resection was sometimes considered as well. The rendition of such prediction models in interactive web-based programs or smartphone apps is becoming pervasive. Prediction of symptoms improvement, ODI score, disc herniation recurrence, or patient satisfaction after spinal decompressive procedure has been reported, as well as accurate prediction of motor improvement after electrode placement for DBS for Parkinson's disease. We live in an era in which wearable digital devices are present and active for the majority of time in an average person's day. Smartphones in particular are an integral part of daily life for the majority of both healthy and ill populations. By 2022, there's expected to be 1.5 mobile devices per capita and a total of 12.3 billion mobile connected devices. On one hand, these devices allow an improvement in the provider-patient communication. In neurosurgical perioperative care, it has been shown that using smartphone-based applications improve compliance to instructions and satisfactions of patients undergoing spine surgery. These applications, in fact, allow the patient to answer health-related questions directly on their phone more frequently anywhere in the world with no need to come to the hospital. On the other hand, devices like smartphones, pedometers, smartwatches are able to acquire and store an incredible amount of data with very small or even no patient participation, thanks to the variety of sensors they're equipped with and their wide connectivity. Systems like accelerometer, gyroscope, skin conductance sensor, heart rate sensor, global positioning systems, call and text logs, Wi-Fi and Bluetooth connections produce every day a wealth of information, estimated to be 1 gigabyte per month per person for smartphones alone. These data have the potential to inform on some key aspects of body health, psychological and social wellness, quality of life in an extremely detailed way. Custom algorithms have been implemented to follow spine patients after surgery to try to correlate possibly acquired mobility patterns to patient-reported pain level. The authors found that pain level and mobility are inversely correlated. This is not surprising, but what is really interesting is that exploiting this new type of data, they were able to lay the basis for an objective measure of a metric, pain, which has always been acquired as a subjective patient-reported outcome. Other algorithms demonstrated the ability to predict hospital admission of schizophrenic patients based on smartphone data, potentially empowering effective strategy for psychotic crisis de-escalation. With the technological advancements brought about by research in AI, applications regarding practice of surgical maneuvers for training purposes have been investigated. Given the potential for inadvertent injury to delicate and vital anatomical structures and the need for refined manual skills in neurosurgery, research regarding training settings and physical or virtual simulators has been prolific. Exploiting virtual reality technology, where the environment in which the person is immersed is completely computer generated, surgeons can practice multiple times on different anatomical and pathological scenarios, overcoming the intrinsic limitations of physical models. A simulator developed specifically for neurosurgical procedures is the Dexoscope. Various centers report having successfully employed this system or modifications of it, obtaining enhanced training, assistance in preparing for difficult cases, and helpful rehearsal of surgical maneuvers. Limitations of available simulators mainly relates to their often inadequate representation of touch, the haptic feedback, and the possible modifications derived from user manipulation of represented structures. Some of the limits and risks related to the development of thinking machines are shared throughout the different fields where AI finds application and big data are used. Neurosurgery makes no exceptions and, as a field related to patient care, deserves some additional specific considerations. The two main limiting factors in the development of ever smarter software are computational power and storage space availability. Thanks to the implementation of the recent cloud resources, power and space are widely available, and in an amount unthinkable just some years ago, and the main limiting factor becomes the cost related to it. Since the algorithms learn from the given input, the higher the quality of the input is, the higher the performance in producing the output will be. This concept is well expressed by the colloquial diffuse expression garbage in, garbage out. To have high quality data means that a considerable amount of time and resources need to be spent in data acquisition and cleaning. One important limitation relates to the difficulty in finding fruitful collaboration. What usually happens is that the clinical expert has the data, but not the computer knowledge and skills to produce a performing algorithm, whereas the computer scientist has these skills, but not the data. The collaboration between these two key figures is increasing over time, but is still limited by the scarce overlap in the understanding of each other's field. The implementation of intelligent systems in patient care brings also some real risks. First of all, as algorithms become more performing, matching and surpassing humans in their own tasks, there could be the tendency to entrust the machine too much. The software, even if it's really good in what it's doing, is not really aware of the fact that it's contributing to patient care, and more importantly, of its consequences. The physician needs to always retain the responsibility for the final decision and to stay in charge of the diagnostic and therapeutic process. An insufficient collaboration between computer scientists and clinicians, as depicted above, can also lead to waste precious resources in trying to answer clinically marginal or irrelevant questions or using the wrong tools to answer them. This slide presents a useful algorithm that summarizes the main steps you need to take and the elements you need to consider to go from an idea of a project involving AI and big data to its actual implementation in clinical practice or research lab. Given the outstanding results that AI applications are producing in neurosurgery and in medicine in general, there is no question that this system will soon find their way to the clinical practice. In neurosurgery, where such diverse types of data are constantly produced and machine learning applications have great potential, we need to make an additional effort in trying to familiarize ourselves with this type of technology, including it in the training of young surgeons beside the essential traditional medical and surgical curriculum. In a field dominated by big, data-driven companies, medical and academic institutions have the big responsibility to team up and invest energy and resources into the development and understanding of AI and its applications, ensuring rigorous clinical validation before bringing them into practice, as well as providing adequate updates to clinically implemented systems. In a world where the patient-physician relationship is already being dehumanized due to ever-increasing time constraints and digitization, the implementation of AI systems in the routine clinical practice has the potential to both worsen this scenario, assigning the patient to a machine, or, on the other hand, to dramatically improve it, automatizing and expediting some mechanical tasks, improving diagnostic accuracy, and doing so, allowing the physician to focus on the very person in front of him. Depending on how we decide to shape it, the future of AI and big data in neurosurgery can be really bright. The evolution of these algorithms has the incredible potential to radically transform patient care and both patients' and physicians' daily care experience, as well as to contribute to marvelous scientific discoveries.